So, good morning. It's the 21st of June, the longest day of the year, and we have the 11th lecture in parallel and distributed computing. And this here will be more or less the last lecture of this type. So first I have to make this an announcement that next week neither of the two of us will be here, and so unfortunately the entire thing has to be cancelled because we have no replacement. That's not too bad because we went through all the stuff that we wanted to talk already, and what we'll do in 2 weeks, we'll discuss one of the previous exams. So I'm extremely busy, and I'm not right here, but I think I will, at least before Friday, I will distribute an exam sheet from last year, and then you can have a look, and then we'll discuss this in 2 weeks. So this will happen in 2 weeks. Next week there is nothing, and today also, I have to leave early, unfortunately, so we'll have only a brief lecture, and then we'll have you trying to implement something, and we'll also try to change the system here a little bit, but more about this later. So now, more or less, we've covered what we the different programming models, and what we are talking about today is one possibility what you could do if you wanted to combine different of these things or in a heterogeneous way. So there's of course several things how you can combine these, but today we want to talk about not like multi-level parallelization, like combining OpenMP and MPI. This is of course also possible if you have systems with multi-cores and you want to combine them. But the idea today is you may not know beforehand what machine you have, and you want to write your program such that it, for example, runs on CUDA, and if CUDA is not available, you want to run it, for example, with threads. Yeah. So, and the question is, how could you do this? Okay. So there will be mostly an exercise today, and we'll start here from this matrix multiply.CUDA, but we'll come, which you find in the lecture 11 folder, but we'll come to this in a minute. So, okay. First things first, so there's a few things that we still have to add to our knowledge about CUDA. So we discussed about CUDA that there are device functions and there are global functions. Yeah? So global functions are the kernels that get called from the main, or from the CPU, from the host, which is the CPU in which the GPU is located. So this can call, for example, here, where is it? Yeah, so this add here, this is a global function, so this is a kernel, and this has to be started with this number of blocks and number of threads like this. And then we have introduced what we call a device function, and the device function is a function that can be called from a kernel, but it cannot be called from the host directly, because the device function is a function that runs on the device, yeah, and it is called from the device. Now, CUDA offers us to specify a second keyword here, which is this host, and which we can add to the device. So we'll have host and device. So So host device functions are functions that can be called from the host and from the device. Yeah, but you need to be careful because when you call them on the host, they will run on the host, and if you call them from the device, they will run on the device. But this is something that's very important to remember, not only to know where they are running and how fast they would be running, but also to know, in order to know to which memory they have access. Because when they are on the host and on the device, they run in different memory space. Yeah? So the host function has only access to host memory, and the device function has only access to device memory. Yeah? So this is very important to remember. Okay, so this host device function, so what actually happens is, and that you specify a host device function, is that the compiler compiles this twice. Yeah? So it's just the idea. I don't. I have my function, yeah, and I want this to run both, sometimes on the GPU and sometimes on the host, and I just don't want to write it twice. Yeah? The compiler compiles these things twice, once for the device and once for the host. It will be completely different programs, yeah, because they are different. There's different hardware, of course. So, okay, and now, if you intend to run to write a program that can run either on the GPU or on the host, yeah, because you want to you're a company, you want to deploy something, and you think, okay, CUDA is a cool thing, we should use this, but then if there's no CUDA available, your program wouldn't run, right? So now you, what you could do is you write your program twice, once for just CPU and once including CUDA, yeah? And now this could be difficult to manage, of course, because then you have the software twice. And now the idea is that you use this host device functions that you simply compile on the host and on the device. Now, problem is the host device function cannot be called from the host as a kernel such that it runs on the device. Right? So whenever you call it from the host, it will also run on the host. But you want to recycle your code. So what you do is, so in the code, so if you want to start something that is running on the device, and you want to run it from the host, you have to have this global keyword. Yeah? So now what you can do is you write your complicated program, so including everything, in a host device function, and you just make a so-called wrapper around this function, which you can then call from your main function in your C program. So this is called a wrapper because it puts a wrapping around the function that you actually want to execute. Yeah? Now, there is, of course, an important difference between a global function and a device function. Yeah? Namely, the device function is always called with a single thread at a time, where the global function is called with many threads. Yeah? And then the global function can identify its threads by asking for the block ID and the block dimension and the thread ID. Whereas the device function and logically the host function does not have access to this data because it has only one thread. It does not know what thread it would be. And the other thing, of course, if you want to run it on the host, then there would not be any thread, right? So it would be just a sequential program. So now what your wrapper then has to do is to identify the coordinates of your thread and hand these coordinates to the host device function. Yeah? So this is what the wrapper usually does. Yeah? So I mean, it of course depends on how you organize your thread and your blocks, but if you take advantage of all of them, then you have 3 block indexes and you have 3 thread indexes. Yeah? And this you can translate to an I, J, and K. And this I, J, and K can then be handed towards the host device function together with the other arguments that the function needs. Yeah? So usually this is the data arrays you're working on. And these are usually the indices in the data arrays you're working on. Yeah? So what the wrapper function has to do is it has to compute these indices and hand it together with the actual data to be processed to the device function. So this is what the wrapper always has to do, or the device wrapper, and then also there needs to be a host wrapper. Yeah. So you also need this to do this on the host, especially if you want to have a different kind of parallelization here. Okay, so in this scenario, we assume that there is no parallelization on the host possible, which in the example that we do later will be different, because here, of course, you can also use C threads, yeah, in order to parallelize this function here. But if there is no parallelization available, what you have to do is what you usually do, you put the thing in loops, right? So this function here would then get, for the I and the J and the K, it would get a minimal value and a maximal value, yeah? And then it would simply have this triple loop from the minimum to the maximum, yeah? And then call the host device function with these indices, yeah? So now these two things would do the same thing. The one would do it on the GPU, the other one would do it on the CPU. Yeah? So, and in principle, all you need to do in order to make this run is to write your host device function and write these two wrappers, and then you do a checkup in the beginning of your program. Is a GPU available? Then you run that. No GPU available, then you run the other one. Okay? So this is in principle how it works. So now you could also have, okay, so we'll do a little bit of strange example here, because in the example we will touch in a minute, we'll try to divide our problem into 2 parts, where we run one part with CPU threads and one part with GPU threads. Yeah? Usually, this is not a good idea, because when you have a GPU available, then the GPU is so much faster then that you don't bother with using the CPU at all. Or you use the CPU for something completely different. Yeah? But just for the exercise, we try to run the same thing, partly on the CPU and partly on the GPU, okay? For the exercise of this. Now, if you do something like this, or either for the exercise now or in reality, because so you do part of your program on the GPU and you do part of the program on the CPU, potentially doing different things. That could, for example, also happen if you use a, what is it called, a high order programming language. For example, you use MATLAB, yeah. So and this MATLAB can use GPU, yeah, but MATLAB may not use GPU for everything, yeah. So if you do some things on the GPU and some things to do on the CPU, then you may have a problem, especially if you use managed allocation, which of course you would always do when you use a high order programming language like MATLAB, because you don't actually see what is going on, right? So because so these things are always developing, and what I'm saying is maybe no longer completely true for the newest generation. And we know, for example, the M1 chips, this is not CUDA, but M1 chips in Apple, they have a common memory space between GPU and CPU, so they can all access the same memory, so they don't need to copy. Yeah, but in general, the hardware thing looks like this. There's a CPU. It has its own RAM, there's a GPU, it has its own RAM, and in between there's something that's called a PCI bus. Yeah? So, and when you do this allocation, we have talked about the managed allocation, where you can use the same data in the CPU and in the GPU. The reality is the data exists twice. Yeah? So there's a copy of this here and there. And now the problem is, if you deal with the copy on the GPU and then you do something with the copy on the CPU, what your computer has to do is it has to migrate potentially the entire matrix, depends on how intelligent it is. Yeah, it has to migrate the entire matrix to the CPU to do the thing, then you migrate it back to the GPU. So if you do any heterogeneous programming, yeah, where you're not running all your program on the CPU, but not all the program on the GPU, and you used managed allocation, you have relatively little control on how much the data is copied. And, this is, usually we do parallel programming because we are dealing with lots of data, yeah, and we may have a big matrix, and if you just want to change a little thing in this matrix on the CPU, yeah, it's always copied back and forward, which potentially is much, much, much more expensive than what you gain by parallelizing your code. Okay? So for that reason, you can be very surprised, yeah, how little you gain when you do when you do this. So this this problem is called memory trashing. So you access memory from two different places. So you always get you always get a miss. Yeah. So this also works. That's also a case with caches. So you try to access your memory from the CPU, and then your program tells you, well, wait a minute, the GPU has done something to this data. We have to copy. Yeah, and then the copying is going on and on. So this is called memory trashing, which we have to avoid. Right. So now we're coming to this is almost all that we had with regard to the lecture, and now this is just a little update. By the way, just remembering, I have forgotten something, and I've forgotten this last time. And I've also forgotten it in the program that we wrote. Yeah, so this is very important. So I marked it in red to remember me, and I still didn't remember it. Okay. So when we call this, when we call a global function, like this add function here, this will return immediately. So you always have to remember what is graphics card actually good for. Usually this is a one-way thing. Yeah. So you tell your graphics card to display something on the screen, and you never expect something back. Yeah. So this is where development of this comes from. So you just send something, and the function will return immediately. Yeah. And you go on doing your stuff. Yeah. And usually, if things is about displaying data on the screen, if something takes too long and doesn't happen before something else is sent after it, it's discarded. It's not a big deal. Yeah, it's like if you have a pixel problem in your screen, you will probably not notice it at all, right? But if you want to do scientific computing with this, then you may have a problem. And the problem would be if you start your program and then you do something with the data, or you terminate your program, yeah, or you try to reload the data from the GPU, then it may not have been yet synchronized, yeah, or terminated, yeah. So therefore, you should always call CUDA device synchronize, which is a barrier that waits for this function here to terminate. So we have skipped over this in the last example, and usually you will not notice that you skipped over this because the threads are so fast usually that this doesn't run into problems, but you should do it anyway, and I've forgotten to do it. So let's have this here. Okay, now we come to our task, and the task is the same that we had last time. Last time we implemented this matrix multiply.cu, and I copied this again to the folder lecture 11. And now what we want to do is, so that the CUDA is already implemented in this, but the CUDA is done here by a global function. Now we want to implement wrappers for CUDA and for CPU threads, so that in the same program we can run it with CUDA and with threads, or even both of them at the same time, partly with threads and partly with CPU threads and partly with CUDA threads. So one thing I've noticed that we have to make sure is that in the job file we have to enable that we have all the 20 cores that our processor had, because otherwise, when we request only one core, we can run only one thread. So this is okay. This took me some time preparing this to notice why it's not getting any faster. Okay, so this is one thing, and in also doing this. Okay, this is not absolutely necessary, but would be if you want to run your program efficiently, then you also have to consider that there is a big difference between the threads in the CPU and the threads in the GPU. Yeah. So what you could say is that the threads if you think about physical threads, then the thread in the GPU should be much thicker than they are in the GPU. Yeah? So the GPU is designed such that it can handle many, many, many threads. So you will hand the simplest thing that you can do to its individual thread. Yeah? On the GPU, on the CPU, you will not do it like this, because making a new thread is very expensive, and then you have only 20 cores instead of hundreds or thousands on the GPU, right? So ideally, so the optimal way would be to have just 20 threads and let these 20 threads do 1/20th of all the work, right? So then, if you remember the implementation that we had, where we put one intro of the C matrix with the matrix multiplication to one thread on the GPU, that would not be a very clever way to do things on the CPU. Yeah. Okay, so that's okay. So this is first of all implement these things, and then we come to the actually interesting challenge. Yeah, where so you remember the things where we splitted this up for MPI parallelization. Now the idea here would be the following. Okay, I don't know why this is A3. It should be A2. Yeah, forget the numbers. Yeah, sorry. Yeah, so the challenge is, of course, we multiply A times B and we get a matrix C, right? And now the idea is that we do this partly on the CPU and partly on the GPU, and we take the first part on the CPU. So we have, for the B matrix, we have to have a copy on the CPU and on the GPU. We'll always have a copy of the matrix A on the CPU, because this is where we assemble everything. Yeah? But we'll take only part of this matrix and then it to the GPU. Then we will use only part of the A matrix to compute part of the C matrix, but on the CPU, but we have to allocate the complete C matrix, yeah, because this is where the matrix in the end ends up, so that we can post-process it, right? And then we compute part of this product on the GPU, and then we copy only the part that we have computed back to back into the C matrix, and then we are done. So, just for the challenge of this. Okay, now this is something that now you are supposed to do, and the thing is, we have been wondering, I mean, we have not yet seen your comments of the lecture, but we have been wondering whether the way we usually do this, that we leave you 20 minutes or 40 minutes, and then you do something or you don't do anything, I don't know, and then I present everything, whether this is the most useful way of doing it. I mean, it has the advantage that I can make a recording and then you can look at it later. And as I noticed last time when I made a lot of mistakes, then these videos where I make a lot of mistakes, they are very popular on YouTube. And the ones where I make less mistakes is, they are not so popular, apparently. Anyway, we decided we try something different today, so we'll not go any recording, so sorry for people not being here. Yeah, so they run try today, but the idea is that we put one of you on this desk and, okay, for let's say 10 minutes or so, yeah, and so everybody, the one who is sitting here is the one who is typing, yeah, and the others should direct him. So I could say him because we are only male here today. And the others would tell him what to do, and then we'll change through, right? So this is an experiment to see whether we this works better. Yeah, and apparently, in order for this to work in the first place, I have a little bit. I tried it out. Of course, Konstantin and me are trying to push you. Yeah, because unfortunately, I have to be gone in. So from now we have exactly 2 hours. Then we'll have to finish this. Okay. Do you agree with this? Yes. So I'll go stop the recording now.